Okay. Still the topic about basic spline functions. Have a review about this space. We have a basis. This basis. This basis consists of powers. All the elements in the basis are powers. The value of a power can be very large or very small. As a result, if we use this basis to solve spline interpolation problem, linear systems, the resulting linear system usually is sensitive to round-off error. So therefore, this basis is not good computationally. Okay, so this is why we turn to find a new basis. In the new basis, we hope low power of this form. Okay, low power of this form in the new basis. To construct a new basis, we go by 2 steps. To construct a new basis, we go by 2 steps. Step 1, we first construct basic spline functions. Basic spline functions, their domain, they define on the whole real line. And then step 2, construct a basis from a basic spline functions. We usually call them B-splines. Then step 2, construct a basis for this space from B-splines. Okay, 2 steps. Now I define B-splines. We begin with extending the knots T0, T1, Tn to an infinite sequence of knots. And based on this infinite sequence of knots, we build B-splines. T0 less than T1, less than T2, and less than Tn. Then less than Tn plus 1, less than Tn plus 2, and so on. Okay, yeah. Extend these knots to infinity. On the left side, T0 greater than T-1, greater than T-2, okay, greater than, and so on. Yeah, extend the knots to negative infinity. Now, based on this sequence of knots, we define B-splines. The first B-splines are degree zeros. B-splines of degree 0. The notation is a B degree 0. So B0, I is the index of one subinterval. The definition of BI0 is the following. BI0, it is a function. When x is in this subinterval ti to ti plus 1, open. Okay. Function value is 1. When x is not in this interval, function value is 0. The graph of this function is this. X-axis, y-axis. Suppose Ti is here. Ti plus 1 is here. Then function value over this interval is 1. So horizontal line. The left end put a closed dot. The right end put an open dot. Okay. Over this interval, function value is 1. And any x not in this interval, function value is 0. 0. Yeah, this is the graph of this is a BI0. Yeah, this is a B-splines of degree 0. As we saw in the last class, BI0 has some quite obvious properties. Number 1, right? Function values non-negative for any x, non-negative. Number 2, the support of B of this function. Support means the set of x values. Okay, where the function non-zero. Okay, yeah. The support of this function is this interval. Over this interval, function non-zero. So the support is this. Yeah, it's this. C. Sum up of this B-splines. I, the index I, goes from negative infinity to positive infinity. Because BI, the support is a finite interval. Actually, this infinite sum essentially is a finite sum. It is a finite sum. It is equal to 1. Okay, for any x. For any x, the sum of these B-splines is 1. Okay, now this is the starting point to construct B-splines. For degree higher than 0, the B-splines are defined recursively by the following formula. Okay. Yeah. Okay. This is number 2. Number 2. B-splines of degree k greater than 0. Okay. Higher degree B-splines. The formula is BIK is equal to x minus TI. Yeah. This I is this I, okay? BIK related to TI. And over TI plus K, right? This K is this K. Minus TI, yeah, times BIK minus 1. Then plus TI plus K plus 1 minus X over TI plus K plus 1. TI plus 1. B K minus 1. I plus 1. X. Yeah. X. Yeah. This is the definition about higher degree B-splines. Say for example, where K is 1, 2, 3, and so on. Say for example, when K when K is 1, then B-spline of degree 1 is equal to X minus TI over, now K is 1, so K is 1, so this is a TI plus 1 minus TI. And then B0 I plus, here K is 1, so TI plus 2 minus X over TI plus 2 minus TI plus 1. K is 1, so 0. I plus, yeah. Then we can write this expression in detail. Say in detail, okay? In detail, yeah, in detail. When X is in this interval TI plus 1. Yeah. When X is in this interval, then what is this? The support of this guy is TI I plus 1. The support of this guy is TI plus 1, TI plus 2, right? So when X is in this interval, actually the second term is 0, right? This guy is 0. So, and this guy is 1. When X is in this interval, this guy is 1. So when X is in this interval, BI1, the value is this. Yeah. When X is in the next subinterval, TI plus 1, TI plus 2. Now this time, when X is in this interval, this guy is 0. First term is 0. And BI plus 1, 0, the value of this function is 1. So when X is in this interval, BI1 is TI plus 2 minus X over TI plus 2, TI plus 1. Yeah. When X not in this interval or in this interval, that means that when X is less than TI, or greater than or equal to ti plus 2. The value of this function is 0. Is 0. Yeah. Let me plot the graph of bi1. The graph x-axis, y-axis is function value bi1. Suppose ti here, ti here, ti plus 1 here, ti plus 2 here. Over this interval, function is this. This is a linear function. When x is ti plus 1, function value is 1. Yeah. This point, suppose the height is 1. Yeah. When x is ti, function value is 0. So it is a line joining these 2 points. Yeah, this one and this one. So this is the graph of bi1 over this interval. Now, over this interval, the graph, let me see, also a line. The graph also a line. When x is ti plus 2, function value is 0. Yeah, this point. When x is ti plus 1, plug in ti plus 1, function value is 1. So yeah, a line join this point and this point. Yeah. Then any x less than ti, greater than ti plus 1, 0. So graph elsewhere 0. 0. Yeah. Yeah. This is the graph of this function. Graph of this function. Yeah. So this is a bi1. It is easy to see similar properties about bi1. Yeah, let me make a list. Properties about bi1. Yeah, let me see. Yeah. Number 8. bi1 non-negative, right? Non-negative. Yeah. B, the support of bi1 is the set of x values where the function is non-zero. Where the function is non-zero, from this graph, we can see that x greater than ti, less than ti plus 2, function value non-zero. So the support is ti plus 2, open interval, right? Over this interval, function value non-zero. Okay. C, it can be seen that summation with I from negative infinity to positive infinity, bi1 is 1 for any x. For any x. This is a infinite sum. But because the support is a finite interval, actually this infinite sum essentially is a finite sum. Yeah. So yeah. This is one example about this formula. Okay, now let me simplify this formula. Let me simplify the formula. It is the definition of BIK. BIK X definition. Yeah. x minus ti over ti plus k minus ti b I k minus 1. This formula, this definition, recursively define BIK. Okay. Ti plus k plus 1 minus x over ti plus k minus ti. Bi plus 1 k minus 1 x. Okay, let me rewrite this vector. Ti k minus 1 I x. Let me rewrite this vector, the numerator as minus this is ti plus 1, no, ti plus 1, minus ti plus 1 plus ti plus 1 minus x, then over ti plus 1 plus k minus ti plus 1. And t, not x. Okay, now let me split this quotient as a sum. 1 minus x minus ti plus 1 over ti plus k minus ti plus 1. Okay, now I introduce a special linear function. Yeah, let me use this notation v k I. Yeah, this function related to I and k. I use this notation to denote this linear function. K minus ti. Then let me call this equation equation 1. Then equation 1 becomes this is the definition of BIK. Then BIK is equal to VIK x BIK minus 1 x. Then plus 1 minus, let me see. Did I copy? I miss something here. Here should be plus 1. Plus 1. Plus 1. Okay. So this quotient, by using this notation, it is a VI plus 1 K. Yeah. So this is the definition of BIK. BIK. Or we can drop x, just simply write this equation as BIK is equal to VIK times BIK minus 1, then plus 1 minus VI plus 1K times BI plus 1K minus 1. Yeah. This is the definition of B-spline of degree K. Yeah, degree K. In general, we can prove BIK so defined is a piecewise polynomial function. Is a piecewise polynomial. The polynomial, the degree is K. Yeah. And also we can prove that BIK is smooth. Actually is a smooth of order K minus 1. Of course, BIK defined on negative infinity to positive infinity. Yeah. Actually, these two properties is in one of the lemmas I present below. Okay. Now about BIK, B-spline of degree K. I make a list of some properties about them. Okay. Yeah. Here is a list of properties. I skip the proofs. Okay, for the proofs, you can take a look at the book. A list of properties about a BIK. Okay, about BIK. Yeah. Okay. All are lemmas in the book. The first one. This property is on positivity of B-splines. A, when K is 0, B-splines of degree 0, it is greater than 0 on this interval. And equal to 0 outside this interval. And BI0 X is 0 outside this interval. So BI0 non-negative. How about for general K? BIK. Here K, I assume greater than 0. When K is greater than 0, then BIK greater than 0 on this interval Ti to Ti plus K plus 1. And BIK 0 is 0 outside this interval. In other words, this interval is the support of this function. So, yeah, this property says that B-splines are non-negative functions. And number 2, about this interval T0 to Tn. Yeah, actually, this interval is the interval that we are concerned. Okay, it's the interval that we want to know. Okay, about this interval, only we have so many B-splines, but only the following B-splines are not always 0. Yeah. Over this interval, only the following B-splines, not always 0. Other B-splines over this interval, always 0. Okay. Depends on the degree. When k is 0, then the following spline functions are not always 0. B 0, 0. Yeah. This function is non-zero at some point in this interval. B1, 0. B2, 0. And Bn minus 1, 0. Bn 0. Yeah. Only these n plus 1 spline functions of degree 0 non-zero over this interval. Then how about when k greater than 0? When k greater than 0, then the following B-splines non-zero over this interval. Which one? Negative k. I is negative k. Yeah. K. B negative k plus 1. K. B negative k plus 2. K. Yeah. Increasing is subscript to n minus 1. K. Yeah. How many functions here? This is n minus 1 minus negative k, then plus 1. Yeah. So this is n minus 1 plus k plus 1. Oh, n plus k. Yeah. Only this n plus k spline functions on this interval non-zero. Other spline functions 0 everywhere on this interval. Yeah. This is a property. Yeah. Property number 2. For the proof, you can take a look at the book. Number 3. This property is on unity of B splines for all k greater than or equal to 0. K is the degree of the polynomial on each subinterval. Okay. For all k greater than or equal to 0 and all x is in the domain of B-spline. The domain of B-spline is from negative infinity to positive infinity. We have summation I from negative infinity to positive infinity. BIK X this infinite sum actually is a finite sum because support of B-spline functions are finite. So actually, this is a finite sum. The summation is equal to 1. Yeah. For any k. Yeah, this property is very important. Very important. Why I say that this property is very important? This property essentially says that BIK for any x, the value of BIK always non-negative and less than or equal to 1. So when we use BIK, when we construct a basis from BIK, the elements of the basis, they don't blow up to infinity, right? It doesn't like x to k. X to k, this power can be very large or can be very, very small. As a result, the resulting basis very ill condition. But now, guarantee, okay, if I construct a basis from BIK, then all elements in the basis, they don't blow up to infinity, okay? It's bounded by 1. So as a result, we solve spline problems to get a linear system. The elements, the entries in the coefficient matrix, they are about the same order in magnitude. Okay, all the entries are about the same order in magnitude. If I construct a basis from spline functions, from B-splines, because of this property. Okay. Yeah, this is a very, very important property. Yeah. Property number 4. This property is about the smoothness of B-splines. Okay. For k greater than or equal to 0, when k is 0, we saw that the graph. When k is 0, yeah, this is the graph. It is not smooth, right? At ti plus 1, the graph has jumps, right? Not smooth. But now k greater than 1, greater than or equal to 1. Okay. The B-splines, BIK, belongs to CK minus 1. Yeah. Smooth. Okay. And the order of smoothness is k minus 1. Okay. When k is 1, 1 minus 1, 0. That means that continuous, just continuous, low derivative. Okay. Property number 5. Property number 5. For k greater than or equal to 2. Oh, this property is about on derivative of BIK. For k greater than or equal to 2, BIK is piecewise polynomial, degree k. So For k greater than or equal to 2, B-I-K-X derivative is equal to this. Ti plus k minus Ti. Bik minus 1 x minus k over Ti plus 1 minus Ti plus 1 times Bi plus 1k. This is a k greater than or equal to 2. How about k is 1? For k is 1, okay, when k is 1, go back to the graph of BI1, the graph. This is a BI1, the graph. From the graph, we can see that this function has derivative everywhere, except at Ti, low derivative, because there is a corner here. Ti plus 1, low derivative, because corner here. And at this point, corner. At any other points, this guy has derivative. So when k is 1, the equation, this equation is true for all x, except x is Ti, low derivative, right? Ti plus 1, low derivative, or Ti plus 2. Yeah. So this property is about derivative of Bik. Now the last property, and also the most important property, number 6. This property is on basis of this space NK. This space the functions in this space, functions are defined, remember, on some interval a to b containing T0, T1 to Tn. Yeah, each function in this space defined on the interval AB. This interval contains this n plus 1 length. Okay, now let me restrict the domain of the functions on this interval. T0, Tn. The following is a basis for this space. Let me explain what this notation, further explain this notation, what this notation means. This notation means S and K restrict the domain to T0, Tn. S and K is a set, and also this is a set. The set of F restrict to Tn K. Okay. What is F? F is a function from S and K. Yeah. If the domain from A to B, now I restrict the domain to T0, Tn. Okay, where F, this notation, means this function. Okay. When x is in T0, Tn. This function is equal to f of x. When x outside T0, Tn, this notation, this function, undefined, low function value, undefined. Yeah, this notation is called the function with the domain, restrict the domain from A to B to T0, Tn. So this notation S and K, T0, Tn, this notation means the functions restrict to the domain T0, Tn. Yeah. Okay, a basis for this space is a basis for S and K restrict to T0, Tn is the following is BIK. BIK, this guy, the domain is from negative infinity to positive infinity. Now, restrict the domain to T0, Tn. Yeah. Where the index I goes from negative K to n minus 1. Yeah. So in this set, how many functions? We have? How many functions we have? We have n minus 1 minus negative K, then plus 1. Let me see. N minus 1, then negative, positive, and then plus 1. Oh, n plus 1. Yeah, this basis has n plus k, so many functions. Therefore, dimension of this space is equal to n plus k, because the basis contains n plus k elements. So the dimension of this. Okay, it turns out that B-splines, some B-splines, not all, some B-splines form a basis for this space. B-splines have nice property. They don't blow up to infinity. Yeah, they bounded by 1 and greater than 0. So the resulting linear system, all the entries are about the same order in magnitude. So the resulting linear system is well-conditioned linear systems. You can accurately to get solutions. Yeah. So in practice, nowadays, we usually use B-spline, use this basis to do computation.